In this video, we're going to be looking at calculating the Fourier series formula coefficient for a function which is neither even nor odd. So this might come from an example in which case you're only given half the interval. You're only given 0 to L instead of negative L to L. And so we've extended the function to just be 0 in the missing interval. And what this is going to do is it's going to destroy the symmetry. And so we're actually going to need to integrate this, we'll need to actually get values for A0, AN, and BN. We'll need formulas for all of them because in order to create a solution which is not either even or odd, we are going to need combinations of even and odd terms. So we're not going to get some of the things that we've seen with even and odd functions where one of the coefficients cancels out. Here we're going to end up getting all of them. Now in this example, L is 1, since our interval is going from negative L to L, negative 1 to 1. So let's start with our A sub 0. And if we're going to integrate from negative L to L, we have a piecewise function. So that's going to mean that if L is 1, for f of x, then we're going to end up with 1/2 the integral from negative 1 to 1, or negative 1 to 0 of 0 dx, because that is the first piece, and then also integrate from 0 to 1 the value of our second piece, which is x. So this thing is obviously all 0. And so if I do my antiderivative here, I'm going to get x squared over 2, and going from 0 to 1, that's going to give me 1/4. Because x squared is 1, and so that'll be 1/2. And when I plug in 0, I'll get 0. So 1/2 times 1/2 is 1/4. Super. Now, basically, we're going to have the same problem that we're going to have to deal with for all of these examples. So again, we're going to have L is 1. Super. But when I plug in my f of x, I'm going to be integrating from negative 1 to 0 of 0 times this piece plus the integral from 0 to 1 of x times this piece. And so obviously integrating 0, I'm going to get 0. So this is the only piece I have to worry about. This is not a symmetric interval, so I can't use any properties of even or odd functions. I just have to go ahead and integrate it. And L is also 1. So this will just be n pi x and n pi x. And integrate this, we're going to need integration by parts, but fortunately only for one step. So dv cosine n pi x dx du is dx, and v is going to be 1 over n pi sine n pi x. And so uv is going to give me x over n pi sine n pi x minus, and now I'm going to integrate v du, which is just the integral of this, and the antiderivative of that, the antiderivative of sine is going to give me a negative cosine, so it'll become a plus, and then I'll also have to divide by another n pi. And we're going to evaluate that between 0 and 1. And if I put in 1 in this, I'm going to get 1 over n pi, but sine of 1 pi x is 0, so that's out. And if I put in 0 for this, I'm also going to get a 0, so that's out. If I put in 1 here, I'm going to get 1 over n squared pi squared cosine n pi. And then if I put in 0, 1 over n squared pi squared, I'm going to get cosine of 0, which is a 1. So I've got a 1 over n squared pi squared, and cosine of n pi is negative 1 to the n minus a 1. And so I can't really leave it like that. I have to figure out what the rule is. So when n is 1, then this is going to be 1 over pi squared. And it'll be negative 1 minus 1, which will be negative 2 over pi squared. But when n is 2, then this will be 1 over 2 squared pi squared times 1 minus 1, which will be 0. And then when n is 3, then this will be 1 over 9 squared pi squared negative 1 minus 1, which will make it a 2. So negative 2 over 9 squared pi squared. And this pattern will continue so that even terms will give 0, and odd terms will reduce to minus 2. So that means our a sub n are going to only be only going to be odd terms. So it'll be 2n plus 1 let's do 2n minus 1, since if we start at n equals 1, which is what our original summation formula indicated, although we could change that as we redo the formula. But 2n minus 1 would be our odd number. We would have negative 2 up top, and then that would be odd number squared pi squared. And again, the 2n minus 1 is odd, starting with n equals 1. And then we would also have to match the cosine coefficients. So inside, the ends that are on the inside, the even ones are being multiplied by 0 coefficient. So all the even ones are gone. All right, so we'll come back to that. Now let us then continue on with the b's. So this is the b sub n formula. And again, we'll put in our ones. And the 1 over here will just give me n pi x. And if I put in my f of x function, I'm integrating from -1 to 0 of the first piece, which is 0. And then integrating the second piece, x sine x. So obviously, again, this part is 0, and then this is the only one that we're going to be integrating. And for that, we're also going to need integration by parts. And then du will be dx, and v becomes negative cosine n pi x and 1 over n pi. And so when we evaluate this, we get x, negative x over n pi cosine n pi x minus the antiderivative duv. So dx doesn't do anything. Minus a minus is going to give me a plus. And then when I integrate this, I'm going to get a sine and another n and pi. So 1 over n squared pi squared sine n pi x. And then again, all of this evaluated between 0 and 1. And let's see, that's going to get me negative 1 over n pi cosine n pi plus, when I plug in the 0, I'm going to get a 0. And then plus, anytime I put in an integer multiple of pi here, when I plug in 1, the sine of n pi is 0. When I plug in 0, sine of 0 is 0. So 0 and 0. And so I just have negative 1 over n pi. And I know that cosine of n pi is negative 1 to the n. And so absorbing the other negative 1 to the n plus 1 divided by n pi. And those are my b sub n's. So let's go back and grab our Fourier series. And we're going to use L equals 1. So when L is 1, these become these. We calculated the B sub n's to be this. And we calculated the A sub n's up here to be these, but only for odd multiples of cosine, odd multiples of pi. And then our A sub 0, I believe, was 1/4. Yes, it was. All right, so then what does this look like when we start estimating? So we've got 1/4. And if I put in an even multiple, let's pull this negative up here just to make it a little less weird looking. So this will be negative, and it's always going to be negative for the cosines. So when n is 1, I'm going to get 2n minus 1 is 1, and 2n minus 1 here is 1. So it's going to be -2 over pi squared cosine of pi x. And then when n is 1 in the other one, we're going to get also a negative, and then 1 over n pi sine pi x. And then cosine will always be negative. So next odd number would be 3, so it'd be 9 pi squared. Again, because it's 1 squared and then 3 squared and then 5 squared, etc. Cosine 3 pi x. And then sine will be plus n. This was a 1. And so this is a 2 pi sine of 2 pi x. And if I do another minus, just to catch up with the frequency of the cosine, we're going to get negative 1 over 3 pi sine 3 pi x. And so forth, ... Now, again, let's double check and see how this works graphically. And part of the great reason for graphing things is that I did have a sign issue. -1 to the n plus 1. When n is 1, this will be an even 1, so that's positive, then that's negative, then that's positive. And so now if we go to the graph, we can see that as we haven't added as many terms as we could have. In some of the previous videos, I added up to like n equals 6 or something like that. And here we're only up to n equals 3, basically. But you can see that in this region, it is beginning to approximate that flat line. But in this region right here, from 0 to 1, it's beginning to approximate that x function. And if we were to continue adding additional terms, we would begin to see that this would flatten out even more in this region, and again would extend as again, more and more and more of a straight line in this 0 to 1 regions.